Welcome to the third lesson of module 4, which is on torsion part 3. In fact, in the last two lessons on torsion, we have looked into some aspects of torsional moment in a bar. Now, we are going to look into some more aspects of torsion in the bar. Well, it is expected that once this particular lesson is completed, one should be able to understand the effectiveness of cross section between solid and hollow bars subjected to torsion. Now, if you remember, in the last two lessons, we have discussed about the effect of torsion on a solid bar or a bar with a circular cross section having solid section, and a bar which is having a cross section which is hollow tube. And in both the cases, we have seen that how the stresses vary because of the twisting moment. Now, we like to see in this particular lesson that which section is effective, whether the solid one or the hollow one. Also, one should be able to understand the concept of power transmission using shaft and relations between torque and power. Now, this is another aspect which we will be looking into today, is that the shaft or the bars which are used effectively in transmitting mechanical power. We will look into the aspects of that how this power transmission is related to the torque. Also, one should be able to evaluate stresses and deformation in circular bars when they are subjected to twisting moment or the torsion. Well, then the scope of this particular lesson includes that as we would have done in the past, we will be looking into the previous aspects through our question answer session, and also we will demonstrate the effectiveness of sections between solid and hollow bars subjected to twisting moment, and that we will be doing through some examples, and effect of power transmission through shaft and the relationship between power and the torque, and examples for evaluation of stresses and deformation in bars of circular cross sections. Well, let us look into the questions which was posed last time. The questions, the first question was that which section is effective in carrying torsion, and this is what I was telling you, that in the last two sessions or last two lessons, we have discussed the effect of twisting moment on a bar which is having circular cross section, but a solid bar. Subsequently, we have seen the effect of twisting moment in a bar which is hollow tube, and we could evaluate the stresses and the deformation. Now, the question comes that out of these two, supposing if we have a bar which is subjected to maybe the same twisting moment, then whether a solid bar is more efficient than a tubular bar or the other way. Let us look into that, and that we will discuss, we will demonstrate through few examples. Now, the first example which I am going to demonstrate is that a steel shaft is to be manufactured either as a solid circular bar or as a circular tube. Now, we will compare these two cases, we will consider a circular solid bar and a circular tube, and a torque of 1500 Newton meter is to be registered without exceeding a shear stress of 50 megapascal and an angle of twist of 1 degree per meter. Now, here we are going to consider that if a bar is subjected to a twisting moment of 1500 Newton meter, and if the maximum stress in the material is not allowed to go beyond 50 megapascal and the angle of twist cannot go beyond 1 degree per meter length. Now, both the criteria or has to be satisfied, then what could be the effectiveness of a solid bar vis-a-vis a tubular section? That is what we are going to compare now. So, what you need to determine is the diameter of the solid shaft. In the first case, this is the part A. Part B is that you will have to determine the outer diameter of the hollow shaft if thickness is 1/10 of outer diameter. So, the inner diameter is given in the process, outer diameter if it is d, the inner diameter is 1/10, I mean the thickness is 1/10 of the outer diameter. Hence, if we deduct twice the thickness, we will get the inner diameter, outer diameter minus twice the thickness of the hollow tube will give you the inner diameter. what you will have to also find out the ratio of diameters and weights. In fact, these will give us a comparison between the hollow and the solid shaft. So, let us look into this example. If we solve it, now this is how it appears here. Now, twisting moment T is given as 1500 Newton meter, the shear stress not to be exceeded beyond 50 megapascal, and also the angle of twist is 1 degree per meter. These are the limiting values, and it is subjected to a twisting moment of 1500 Newton meter. Now, as we know, the expression that T by J is equals to tau by rho is equals to g theta by L. This is applicable for both circular shaft as well as the tubular shaft. Now, out of these, if we take the first part of it, that means T by J is equals to tau by rho, then we get the relationship this we have seen earlier, or if we look into that T by J is equals to tau by rho. Now, for a solid shaft of diameter d, J is equals to pi by 32 times d 4 and rho is equals to d by 2. So, T times 32 pi d 4 is equals to tau times 2 by d. So, this d cancels d cube. So, tau is equals to, so these two cancel 16, this gives you 16 t by pi d cube. So, this is the value of the tau, that is what we have looked into here. So, t is equals to 16 t times pi d cube. So, if we substitute the value of twisting moment as 1500 into 10 to the power 3, and then shearing stress d is limited to 50, that is what is substituted here. So, this gives us to the power 1/3 gives us the value of d, which comes out to be 53.46 millimeter. Also, if we look into, since we will have to satisfy both the criteria, that shear stress cannot exceed beyond 50 megapascal and the angle of twist cannot be greater than 1 degree per meter length. So, if we consider 1 meter length of this shaft, then if we go through this expression T by J equals to g theta by L. So, T again is 1500 into 10 to the power 3, so much of Newton millimeter, J is pi d 4 by 32, G is given as 78 into 10 to the power 3, 78 gigapascal. So, converted into megapascal, into theta, theta is 1 degree. So, 1 degree is pi by 180 radian. So, this is what is used over here, divided by 1000 is the L, and this gives us a value of d is equals to 58 millimeter. Now, out of these two diameter, if we look into that, this much of diameter is necessary, so that shear stress is kept within limit of 50 megapascal. Now, this much of diameter is necessary for theta or the rotation to be 1 degree per meter length. Now, the question is, you will have to satisfy both the criteria, you will have to select the diameter in such a way that it satisfies both the criteria. Now, if we select the lower diameter, then it will satisfy the stress criteria, but it will fail in the rotation, and if we take the higher diameter, which is necessary for the twisting angle, then it will satisfy both the criteria. Hence, the higher diameter is to be selected to satisfy both the aspects. So, the selected diameter in this case will be 58 millimeter. Secondly, if we look into the second aspect, that when you have a hollow shaft, the thickness of which is 1/10 of the outer diameter is d. So, thickness is 0.1 times d. So, the inner diameter then is going to be equals to 0.8 times d. Then the polar moment of inertia J, again same expression should be applicable over here. So, J is pi d 4 by 32, and here d 4 is d outer to the power 4 minus d inner to the power 4, and this comes out as pi 0.5904 d to the power 4 divided by 32. So, if you substitute again T by J equals to tau by rho, this is T and this is J is equals to tau is 50 and rho is d by 2, the outer diameter by 2. This gives us a diameter of 63.73 millimeter. So, this is from the criteria of the satisfaction of the stress. Now, let us look into that if we try to satisfy the rotational angle criteria, that angle of twist should not exceed 1 degree per meter length. Then twisting moment T is 1500, J again we have calculated here as pi times 5904 d 4 by 32. This is equals to G, which is 78 gigapascal times 10 to the power 3, so much of megapascal, into pi by 180 radian is the rotation divided by 1000, and here the D comes out to be 66.03 millimeter. And once again that the diameter which is required from the satisfaction of the stress is 63.73 millimeter, and diameter which is necessary for satisfying the twisting angle is equals to 66.03. So, higher of these two again will be governing, which will satisfy both the rotation as well as the stress. So, since the higher diameter will be satisfying the rotation as well as the stress, so that is the diameter which we will have to select. So, selected diameter in this particular case is 66.03. Now, if we look into, so from this particular comparison, as we can see that we have a circular shaft, solid shaft, which is having a diameter of 58 millimeter, which will satisfy both the stress criteria as well as the rotational angle criteria, and a tubular shaft which is having a diameter of 66.03 millimeter. Now, if we try to take the ratio of these two, the diameter of the hollow shaft to the diameter of the solid shaft, then we find that diameter of the solid hollow is 66.03 and diameter of solid is 58. So, the ratio gives us a value of 1.138. Now, if we take the ratio of their weight, now the weight is nothing but equals to the cross sectional area times the length times the density. So, now area the length and the density being common for both, we take the ratio of the areas. So, weight ratio of the weights is equals to the ratio of the areas, and that if we compute area of the hollow shaft as pi by 4 times d outer square minus d inner square divided by pi by 4 times d square as the solid shaft, then we get a value of 0.47. Now, please note these two values, that the ratio of the diameter is 1.138 and the ratio of the area is 0.47. This means the hollow area is equals to 0.47 times the solid area, and diameter of the hollow bar is equals to 1.138 times the diameter of the solid bar. Now, this comparison states that the diameter in case of hollow bar to satisfy or to resist the 1500 Newton meter of twisting moment, satisfying both the criteria of stress and the rotation angle, the hollow diameter, outer diameter of the hollow bar will be 14% more than the diameter of the solid bar. But the weight wise, since in the hollow bar we do not have material at the core, so naturally the weight wise there is a reduction, and the ratio of the weights between the hollow bar and the solid bar is almost half. Now, the diameter the weight of the hollow bar is 0.47 times the weight of the solid bar. So, you see that though we are utilizing 14% extra in the diameter, we are gaining in the weight, which is in the tune of half the weight of the solid bar. So, evidently that hollow tube gives or is more efficient than a solid shaft, and this will be more clear if we look into the next problem. The next problem states that a solid shaft and a hollow shaft of the same material. Please note that we have the same material, same length and same outer radius. These are identical so far as the material is concerned, it is identical so far as the external radius is concerned or the external diameter is concerned. The diameter of the solid shaft, whatever we have, if that is d, the diameter, outer diameter of the tubular shaft also is d. So, from external appearance they are identical, only thing one is a solid shaft, other one is a hollow one, and the inner radius of the hollow shaft is given as 0.7 times r. Now, if both shafts are subjected to the same torque, if both the hollow and the solid shafts are subjected to the same torque, then compare their shear stresses, the angle of twist and weights. So, three aspects are to be compared, the shear stress, the angle of twist and the weight, and subsequently we will have to find out the strength to weight ratio for both the shaft. Now, this is one important aspect to find out the strength to the weight ratio. Now, by meaning the term strength, we understand that if we take a bar or a shaft which is subjected to a twisting moment, now how much resistance it has to take the twisting moment, that is what is its strength, and weight we have seen, which is the cross sectional area multiplied by the length multiplied by its density, is the weight. Now, the strength wise, so we calculate how much twisting moment it can resist to its weight, that is the strength to weight ratio. So, that we will compare both for the hollow tube as well as for the solid shaft. Now, if we look into the calculations of this, that outer diameter for the hollow tube is given as d, the inner diameter is 0.7 times d, it is given in the form of radius and we are writing in the form of diameter, and the solid diameter is also d, and S stands for, suffix S stands for solid, suffix H stands for the hollow. Now, if this is the external and internal diameter for the hollow one, then the polar moment of inertia for the hollow one will be pi by 32 times d outer to the power 4 minus d inner to the power 4, and d inner is equals to 0.7 times d. So, this gives us a value of 0.76 times pi d 4 by 32. So, this is the value of the polar moment of inertia for the hollow section. Likewise, the polar moment of inertia for the solid bar is pi d 4 by 32. Now, if we compare their shear stresses, the shear stress in the hollow to the shear stress to the solid. Now, as we know that T by j is equals to tau by rho. So, tau, the shear stress is equals to T rho by j. Now, if we say tau for the hollow, the same twisting moment is the same. Now, diameter rho also is the same for the hollow and the solid one. So, if we write in terms of, if we keep T rho parameter same for both, then we have 1 by j, this is j for hollow, and likewise tau s will be T rho, which is constant for both, is 1 by j times s. So, tau h by tau s will be the j for the solid by j for the hollow, and this is what has been done over here. And if we compute this to take the ratios of j h, j s to j h, you will find that this value comes as 1.316. Now, again if we take the ratios of the angle of rotations, which is theta hollow to theta s, and this is again T by j is equals to g theta by L. Hence, theta is equals to T L by g j. Now, all other parameters T, L and g are common for both the shafts, both for hollow as well as for the solid. So, the parameter which is varying is j. So, theta h by theta s is equals to 1 by j h times j s by 1. So, again this is j s to j h. So, if we compute that, that we have seen as 1.316. So, both the ratios of the shear stress as well as the angle of twist, they are dependent on the polar moment of inertia of the shaft, and the value corresponding to that is 1.316 in both the cases, because both shear stress and the angle of twist depends on the ratio of the polar moment of inertia. So, now if we compute the twisting moment, that because we will have to compute the strength to weight ratio. So, we can compute the value of the twisting moment that can be resisted by the hollow section and the twisting moment that can be resisted by the solid section. Now, the twisting moment that can be resisted by the hollow section is equals to tau j by rho. This is from this particular expression, that T by j equals to tau by rho is tau j by rho. So, rho is again equals to d by 2, and j h as we have seen that pi by 32 d to the power 4 minus inner diameter, which is 0.7 d to the power 4, and this gives us a value of 0.15 d cube times tau. And the weight of the hollow bar is equals to the cross sectional area pi d square by 4 times the length times. Now, since this is a hollow bar, so our cross sectional area will be equals to pi by 4, the cross sectional area will be pi by 4 times d outer square minus d inner square, and this gives us a value of 0.51 pi d square by 4, because d inner is 0.7 times d. and length times the unit weight gamma. So, this gives us a value of 0.4 d square L gamma. This is the weight. Subsequently, the twisting moment that can be carried by the solid shaft is equals to again T by j equals to tau by rho. From that we get pi d cubed tau by 16, which is equals to 0.2 times d cube by tau d cube times tau, and the weight of the solid shaft is equals to pi d square by 4 is the cross sectional area times length times unit weight, which comes as 0.785 d square L gamma. Now, if we take the ratios, the T h to W h, that means twisting moment that can be carried by the hollow shaft divided by the weight of the hollow shaft is equals to, we get 0.37 times d tau by L gamma, and twisting moment that can be carried by the solid shaft to its weight is equals to 0.25 times d tau by L gamma. Now, d tau by L gamma, this particular parameter is constant for both the shafts, they are identical, because it is subjected to same amount of stress for the same length, for the same unit weight, and having the same outer diameter. Hence, the values, as we can see, the strength to weight ratio is more in case of tubular section than the solid shaft. And how much is the difference? Difference, if we look into, it is 0.37 minus 0.25 divided by 0.25 times 100. So, this is 48%. So, as we can see that in case of hollow shaft, we have 48% more strength to weight ratio. So, this demonstrates, these two examples demonstrates clearly that tubular shaft is more efficient than a solid shaft. And as you can make out that we had discussed earlier, that from the center as we go away towards the radius, we have maximum stress as well as the contribution of the material in terms of the polar moment of inertia is more in case of tubular section than the solid one, because at the solid one the core part does not contribute much. So, if we take off that particular material, eventually the hollow section becomes more efficient. And in fact, if we go for thinner tubes, that means, if the tubular sections has lesser thickness, then you will see that it will be more efficient in resisting the twisting moment. Well, now the second question was that what is the effect of torsion on bars of varying diameter. Now, so long we were looking into that if we have a bar of uniform diameter and subjected to twisting moment, then what is the effect of such twisting moment on the bars, on stresses and the deformations. Also, we have looked into that if we have a stepped shaft, if we have a varying diameter, then what will be the consequences. Now, if we have a varying diameter, gradually varying diameter of a shaft, then what will be the consequences if it is subjected to a twisting moment. Now, let us look into that. Now, if we take a bar which is gradually varying, and let us say we have a diameter here as d 1, diameter here as d 2, and subjected to a positive twisting moment T. Now, as we know that T by j is equals to tau by rho. So, from this if we compute the shearing stress tau, this is T rho by j, and this in terms of diameter is 16 T by pi d cube. Now, this shows that the shearing stress tau will be higher if d is lower. So, for a lowest diameter we will get the highest stress in such kind of bar. Now, if this particular bar is subjected to a uniform twisting moment, then the maximum stress will occur where the diameter is the least. So, in fact, we do not have to bother for anything else. So, wherever we have the least diameter, corresponding to that if we compute the stress, that will be the maximum possible stress, and in a varying bar diameter, a bar of varying diameter. Now, if we like to compute the value of the theta, the rotation. Now, let us say if we take a section which is at a distance of x, and let us say this small length is d x, then the change in angle between this in the small strip, if we call that as d theta, Now, as we know that T by j is equals to g theta by L, or for this small segment which is of length d x and the rotation angle is d theta, this is equals to T d x by g j. Now, here j is the parameter which is the function of the diameter, and the diameter in this particular case is varying. Now, if this is diameter d 1 and this is diameter d 2, and at this particular point if we say this diameter is say d suffix x, then the value of d suffix x will be, if we draw this length, this is also d 1. So, this balance length is d 2 minus d 1 by 2. So, the length d x d suffix x is equals to d 1 plus d 2 minus d 1 by 2 times x by L, if L is the length of this bar. So, this and since we will have to add this side plus this side. So, twice of that. So, this 2 will get cancelled. So, this is equals to d 1 plus d 2 minus d 1 times x by L. So, this is the diameter d x, and correspondingly the value of polar moment of inertia will be pi by 32 d x to the power 4. So, d x, now this is the function of x. So, if we like to calculate the theta, now we have got the expression d theta is equals to T d x by g j. Now, if we like to compute the value of theta, which is over the entire length. So, integral 0 to L d theta will give us the value of theta, which is equals to integral 0 to L T d x by g. Let me write j as a function of x. Now, j we have computed in terms of d, and d is a function of x. So, j also is a function of x. So, we can compute the value of theta from this particular, if we evaluate this integral, we can get the value of theta. So, for a bar of varying diameter, we can compute the stress for the least diameter, and we can compute the angle of rotation theta from this particular expression. Now, if we have varying twisting moment, instead of having constant twisting moment in the bar, if we have the varying twisting moment, then over the segments, as we have done in the past, that if we have twisting moment which is non-uniform. So, between two such twisting moment, we take the free body, find out how much is the twisting moment, and in that particular segment again we compute the stress, and we calculate the maximum of the stresses in these zones corresponding to the twisting moment, and maximum of this maximum will give us the maximum possible shear stress in the whole of bar. Well, now the third question was that what is the value of minimum shearing strain for solid shaft as well as for the tubular shaft. Now, we have seen the value of the shearing strain gamma is equals to d theta d x times rho, where rho is the diameter, rho is the radius of a segment which is taken out from the solid shaft. Now, this shearing strain becomes maximum when it reaches to the outer periphery, which is equals to r. So, gamma max is equals to d theta by d x times r. When rho becomes r, then it becomes gamma max. So, we can write that gamma by gamma max is equals to rho by r, or gamma is equals to rho by r times gamma max. Now, from this expression you can see that if rho is equals to r, when rho is equals to r, the outer one, r by r, this is 1. So, gamma is gamma max, and when rho is equals to 0, then gamma is 0. So, in case of solid shaft, the minimum strain gamma mean is equals to 0, and gamma max we can compute from this particular expression, the once we know the stress. which is occurring at the outer periphery. Now, in case of tubular shaft, now here gamma again in terms of this, if we write as rho at any radius divided by outer radius here is r 2. So, gamma by rho by r 2 times gamma max. Now, when rho becomes r 2, then the value of the strain is the gamma max, which is on the outer periphery. So, gamma max in this particular case is equals to gamma max at r 2, which is at the outer periphery. Now, for this, since we do not have any material at the core, the material starts at a distance of r 1 from the center. So, the gamma minimum value in this particular case, where rho is equals to r 1 divided by r 2 times gamma max. So, in terms of the maximum strain of the periphery, we can compute the strain at this level, which is r 1 in the ratio of the radius. So, r 1 by r 2 times gamma max is the minimum value of the gamma in case of tubular shaft. So, that is the difference between the strain value in the hollow shaft and the strain in the solid shaft. In case of solid shaft, the minimum value of the strain is 0, which is at the center of the shaft, and its maximum at the outer periphery, and in case of tubular one, the minimum strain is at the inner periphery and the maximum strain is at the outer periphery. Well, having looked into the aspects which in which we have established now that the tubular sections are more effective. Now, one of the applications of these shafts is in transmitting the mechanical power from one device to the other. The shafts are extensively used for transmitting power from one mechanical power from one device to the other. Now, if a shaft or a bar is rotated by a motor, it transmits the shaft moves and it transmits torque to another system. So, it undergoes rotation, and there is a rotational speed which is omega, and it transfers a twisting moment which is t, and the twisting moment which is transferred in the other device from this, it is exactly in the same direction as this angular rotation. Now, that device gives a resistive twisting moment which is in the positive direction, and that is what is shown over here. This particular direction is the positive twisting moment which is acting in the transmitted shaft. Now, this particular shaft is transmitting the twisting moment into the other shaft, and as a resistive moment it is acting in the positive direction, and this is what is demonstrated over here. Now, this rotary motion of the shaft generates power, and this amount of power that is being transmitted, the amount of power which gets transmitted through the rotation of the shaft, it depends on the magnitude of the torque that is applied and the angular speed, the speed of rotation which we call here as omega. So, it depends on the magnitude of the torque and the speed of rotation. In fact, it is the product of the torque and the speed of the rotation. Now, if we look into that, in such shafts, the main problem which is essential to be determined is the size of shaft, so that it can transmit the power at a specified rotational speed, now without exceeding the allowable stress. And this is important, that from design point of view, we need to find out that what should be the diameter of this particular shaft, so that it can transmit the requisite power as we desire, and with a particular rotational speed without exceeding the stress level in this particular material, and that is the purpose. So, we need to find out what should be the diameter of this kind of shafts. Now, since it involved that amount of torque and a constant magnitude, so the work done by the shaft when it rotates, the work done by rotating these shafts under angular speed omega is equals to the torque multiplied by this rotation. So, work done W is equals to torque multiplied by the angle of rotation, which we have designated as psi. So, T times psi is the work done W. Now, power is generally the rate at which this work is done. So, P is equals to dW dt, which gives us, and T being a constant magnitude. So, dW dt gives us W, if you substitute as t psi, t is small t is the time. So, this is equals to capital T, which is a constant twist, times d psi dt, and small t again is with respect to time, and d psi dt is nothing but is a change of angle, change of twist angle per unit time, which is the speed, the angular speed, and that we have defined as omega, which is generally defined in terms of radian per second. So, power p is equals to t times omega. Now, let us look into the units that we use for these systems. Now, power generally is given in watt, and torque is Newton meter, angular speed is radian per second. Now, what is 1 Newton meter per second? Okay. So, that is the unit of the power. What is the unit of the power? And Newton meter, as we have seen, is the unit for the torque, and angular speed is defined in terms of radian per second. Now, many a times we define the angular speed or the shaft which is transmitting power in terms of the frequency, that how many number of revolutions it has. So, 1 revolution per second is called as the frequency or hertz, we call this as cycles per second. Now, 1 cycle, if it moves, in fact it moves over 360 degree, which is equals to 2 pi radian. So, we write this angular speed omega as equals to twice pi f radian per second. So, f is cycles per second or a 1 revolution per second. So, this gives 1 revolution is equals to twice pi radian. So, this is twice pi f radian per second, and hence if we substitute for omega, we get the expression for power p as equals to twice pi f t, and this is the relationship between the power, transmitted power, and the twisting moment t, where f is the frequency at which the shaft is rotating, f is the frequency, t is the torque that is being applied in the other device, and p is the power that is being transferred through the rotation of the shaft. Now, sometimes frequency is used as the number of revolutions per minute, and in short we call this as RPM, the revolution per minute, and is commonly designated with the notation n. Now, since it is revolution per minute, so n by 60 is equals to f, which is cycle per second. So, n is equals to 60 times f, and if we substitute for f as n by 60, we can get the relationship between the power and the revolutions per minute, which is p is equals to twice pi n t by 60. Okay. So, in terms of if the rotation of the shaft is defined in terms of the revolution per minute, which is n, then power is equals to twice pi n t by 60, or if it is defined in terms of the frequency f, which is revolution per second, then it is twice pi f t. Now, sometimes in FPS unit we define the power as the horsepower. Now, 1 horsepower is equals to 550 foot pound per second. So, if you substitute these values of power in terms of, if you write power in terms of horsepower, then T we write in terms of foot pound, and we get an expression that P is equals to twice pi n T by 60 into 550. So much of P is in HP horsepower and T is in foot pound, or roughly approximately the 1 horsepower is equals to 746 watt. So, if we use this relationship, we can relate if the power of a motor is defined in terms of a horsepower, we can convert that in terms of watt, and we can use our relationship that watt is equals to Newton meter times torque multiplied by the radian per second as the frequency or the angular speed. So, this is helpful in relating the transmitted power and the torque, and so when we like to find out the diameter of a shaft which is necessary for transmitting power from one device to the other without exceeding the level of stress, then first we compute that what is the amount of twisting moment that is getting generated in that shaft for transmitting that amount of power, and for that particular twisting moment, as we have seen in the previous sections, how to compute the value of stresses and the angle of rotations, that we compute, and if we know the allowable stress for that particular material, then we can safely say that what diameter is necessary for that shaft, or for a particular diameter whether that particular shaft will be able to withstand that amount of stress or not. Well, now let us look into some of the examples. In fact, these are the examples which I had said last time and asked you to look into. I am sure you have done this. Now, in this a stepped shaft ABCD is consisting of solid circular segments. Now, there are 3 segments over here, the diameter of which are given here. This is 80 millimeter, this is 60 millimeter, and this is 40 millimeter. Now, they are subjected to a torque which is 3000 Newton meter in this particular case, which is according to our notation it is positive, is subjected to twisting moment of 2000 Newton meter here at C, and at D we have a twisting moment of 800 Newton meter, which is also positive. Now, incidentally, all 3 twisting moments in this particular case, they are all positive, which are acting at A, B, C and D. Now, what we need to do is that we will have to find out the value of the maximum shear stress in the shaft and the angle of twist at point D. Now, as you know that we have looked into earlier that to evaluate the twisting moment when they are subjected to a non-uniform tension torsion, that we take free body diagram and compute the values of the twisting moment. Now, if we divide these segments in 3 parts, let us call this segment as segment 1, this part as segment 2 and this part as segment 3, and then we compute the values of the stresses in each of these segments. Since 3 segments are subjected or having 3 different diameters, so they will be having different polar moment of inertia. So, we compute the value of the shearing stresses corresponding to these 3 segments, and the maximum value of the shearing stress in either of these sections will be the maximum possible value of the shearing stress. But when we like to compute the angle of rotation, now because of the twisting moment that is acting in different segments of different magnitudes, now all will contribute to the rotation. Now, here since the sense of the twisting moment are identical or they are all positive, so all will be contributing to the same angle of rotation. Now, as we had seen in the past that when we try to rotate in different form, if one rotates in an anticlockwise form, then it will have anticlockwise rotation. If you have a negative twisting moment in a clockwise form, it will have negative rotation. So, the sum effect of these 2 rotations will be the algebraic sum of the rotational values. Now, let us look into that what will be the value of the stresses in each of these segments. If we compute the values, you will see that as we have seen in the past that T by J is equals to tau by rho is equals to g theta by L. So, if we take the first of these 2 values that T by J is equals to tau by rho, then tau is equals to T rho by J, and this gives us this value as 16 T by pi d cube, which we have seen earlier. Now, we need to compute the value of stress in 3 different segments. For segment 1, we have the values of the twisting moment. If we look into that, the shaft is a stepped one. Now, for the segment 1, we have a, if we cut a section over here, if we take the free body diagram, then we will have a twisting moment as 800 Newton meter. For segment 2, we will have twisting moment as 2800 Newton meter, and for segment 3 we will have 5800 Newton meter. Now, if we compute the values of the stresses corresponding to these 3 segments, segment 1, segment 2 and segment 3. Now, tau for segment 1 is equals to 16 times T, which is 800 Newton meter into 10 to the power 3 divided by the pi times d cube, and d in this particular case is 40 cube, and this comes eventually as 63.7 MPa. Now, for tau for the segment 2 likewise, is equals to 16 into 2800 into 10 to the power 3 divided by pi into 60 cube. The second segment's diameter is 60 and this comes as the value of torsional stress as 60 for the shearing stress as 60.02 MPa. And likewise, the shear stress for the third segment comes as 16 into 5800 into 10 to the power 3 divided by pi times 80 cube, where diameter is 80 and this comes as 57.7 MPa. Now, out of these three, as you can see at three different segments, we have three twisting moments and correspondingly we have three stresses. The maximum stress occurs in the second segment, which is 66.02 MPa. So, out of these three, this gives us the maximum value. So, this is the maximum value of the shearing stress. This is tau max. Now, let us look into the value of the rotational angle theta. Now, as you have seen that T by j is equals to g theta by L. So, theta gives us a value of T L by G j. Okay. Now, for segment 1, if we compute theta, this is equals to 800 into 10 to the power 3 into L is equals to 500 by G is 80 gigapascal into 10 to the power 3 into pi by 32 into 40 to the power 4. So, pi d 4 by 32. So, this comes as 1.14 degree. Now, this will be in radian, and if we multiply that by 180 by pi, that will give us the value in degree. So, this comes out as 1.14 degree. Now, for theta, for the segment 2, theta 2, if we compute exactly in the same form, only we have twisting moment as 2800 into 10 to the power 3 into 500 into 32 divided by 80 into 10 to the power 3 to pi times 60 to the power 4 into 180 by pi, if we multiply with for converting radian to the degree, this comes as 0.0788 degree. And likewise, for third segment theta 3, we get this value as 0.52 degree if we take T as equals to 5800 Newton meter. So, the total rotation theta as we get is equals to theta 1 plus theta 2 plus theta 3, because all twisting moment are in the same sense. So, this eventually comes as 1.14 plus 0.788 plus 0.52 degree, and this is equals to 2.448 degree. So, this is the angle of rotation because of the twisting moment that is acting in the non-uniform section. Well, let us look into the second example problem. In fact, this example also was set last time, that a solid circular bar ABC consists of two segments as shown in figure. Now, what is the allowable torque if the shear stress is not to exceed 32 MPa and the angle of twist between the ends of the bar is not to exceed 1 degree? G is given as 100 gigapascal. Now, here we have one constant torque T, which is acting in this. So, this is the positive twisting moment, and we have two segments which are of diameter 50 millimeter and 40 millimeter. So, shear stress we will have to compute, which will be definitely corresponding to the lower diameter, but it should not exceed 32 MPa, and angle of twist should not exceed 1 degree, which will be combination of theta for the two. Now, let us look into the value of this. Now, again for part T by j is equals to tau by rho. So, we will have to compute the twisting moment, tau is given. So, this is tau j by rho. Now, j for the, now here if we look into that, the part AB, AB is of 50 millimeter diameter and part BC is of 40 millimeter diameter. Now, for part AB, if we compute now as the twisting moment from T by j is equals to tau by rho. So, tau T gives us as tau j by rho. So, T when we need to satisfy the stress criteria, this is equals to tau into pi d 4 divided by 32 times d by 2, which is equals to tau times pi d cube by 16, and this comes as, if we substitute the value tau, we know that it is to be limited to 32 MPa, and that comes as 402.124 Newton meter. And for the second case, that when you have diameter as 50, then T comes as equals to 785.4 Newton meter. So, obviously, you will have to apply this much of twisting moment, so that it can resist both. So, this is the value of the twisting moment. Now, let us look from the angle of twist point of view. Now, theta as we know is equals to T L by G j. So, if we compute the value of the twisting moment, now we have two segments theta 1 and theta 2. So, theta 1 will be equals to T 1 L 1 by G j 1, let us call it as, and this if we write as T times L as 1000 times 32 divided by G is 100 to 10 to the power 3, and J will be pi times 40 to the power 4 pi d 4 by 32, and this comes as 39 into 10 to the power minus 9 T. And likewise, theta 2 if we compute as T, T also is the same twisting moment, only variable is L 2 G j, and that if we compute, which will be 3 into 1250 is the length times 32 by 100 into 10 to the power 3 times pi into 50 to the power 4. So, this comes as 20 times 10 to the power minus 9 t. Now, if we combine these two, that will give us the value of theta, which is equals to theta 1 plus theta 2, and that if we equate to 1 degree, which is equals to so much of pi by 180 radian, and then from this we can get the value of t, and this if we equate this theta, which is sum of this theta 1 plus theta 2 to this pi by 180, it comes the value of t as 295.82 Newton meter. Now, as you can see that we have three values of the twisting moment. This is one which is from the stress criteria, and we have another one from the rotational twisting angle criteria. So, this being the smallest, this will be the guiding twisting moment. So, that it can satisfy both the criteria of the stress as well as the twisting moment. So, the minimum value of the twisting moment will be the governing moment in this particular case. Well, this is another example where we have discussed that if we have a shaft. Now, earlier we had a non-uniform distribution of a torsion having varying diameters of the shaft. Now, if you have uniform distribution of the uniform diameter, but the torques are of different magnitude, then we can compute the value of the stresses. Now, here steel shaft ABC is connected with the 3 gears at A, B and C, and these gears are transmitting moment of 240 Newton meter, 540 Newton meter and 300 Newton meter, and their directions are that 240 Newton meter is acting in this form, whereas 540 is acting in this direction and 300 is acting in this direction. So, these are the 3 directional values, and AB is the solid bar and this is the hollow bar of outside diameter 1.25 times d and inner diameter is d. Bar lengths are given over here, G is 80 GPa. Now, what we will have to find out is what is the minimum diameter d if allowable shear stress in the shaft is 80 MPa, and what is the minimum diameter d if angle of twist between any two gears is limited to 4 degree. Now, let us look into the value of that. Now, if we compute the value of shearing stress, now tau as we know is equals to 16 T by pi d cube. So, if we look into the values of the twisting moment, now here we have 240, here we have 540 and here we have 300. Now, from equilibrium point of view, yes, you can see these two some balances this. So, at this we will have 240 and at this cross section we will have 300 Newton meter. So, if we compute the value of stress for the first one, we will have shearing stress is limited to 80. So, 80 is equals to 16 times, here is 240 into 10 to the power 3 divided by pi d cube. So, from this we get d as equals to 24.82 millimeter. From the second case, if we compute the d from same expression, we get the value of d as 20.23 millimeter. Now, only difference here is that twisting moment is 300 Newton meter in place of 240. So, these are the two diameters we have and highest of these two diameters will be the governing diameter. Now, if we compute from the point of view of the rotation that T by j is equals to g theta by L, then again j is equals to pi d 4 by 32. Now, only second case when you compute the value of d, keep in mind that here the shaft is a tubular one and for tubular one as we know j is equals to pi by 32 d 4 d outer 4 minus d inner 4. This we will have to apply to compute the value of d. And likewise, we compute the value of rotation theta is equals to T L by G j, and from this if we compute the value of d for the solid case, we get d as equals to 22.64 millimeter, and again for j for the hollow one if we apply d is equals to keeping that theta as equals to limited to 4 degree, d we get as 21.85 millimeter. Now, in this particular case as you can see the diameter which we get here as 22.64 is again is the governing. So, in the first case we had 24.82 millimeters the diameter which is to be provided, and in case of this we will have to provide 22.64 millimeter to resist the twisting moment through the gears as it is shown. Well, I have another example problem set for you. We will look into this, we will discuss next time, that a tubular shaft is designed to transmit 120 kilowatt at 15 hertz. The inside diameter of the shaft is to be 3/4 of the outside diameter. Now, if the allowable shear stress in the shaft is 45 MPa, what is the minimum required outside diameter d? Now, this particular problem is similar to the one which we have discussed today, that how if we transmit the power, then what is the diameter of the shaft necessary. So, from today's discussion you should be in a position to evaluate this particular example. Well, to summarize then, that we have in this particular lesson we have demonstrated the effectiveness of a hollow circular bar over a solid circular shaft through the examples, and we have looked into the concept of power transmission and the relationship between the power and torque, and then we have looked into some examples to evaluate stresses and deformation in bars of circular section due to twisting moment. Well, these are the questions set for you, that if a bar made of a material which cannot withstand tension is subjected to torsion, then what will be the effect of such twisting moment? Then what is the relation between power and the torque, and how will you evaluate stresses and deformation in circular bars for indeterminate systems? Well, we will discuss these questions in the next lesson. Well, thank you very much for your attention.